This is a breadcrumb. It's a single node in a wireless mesh. If you turn on more than one, they'll find each other automatically and talk to and through each other in order to deliver packets wherever they need to go. These are our biggest strengths in a nutshell. Rajant breadcrumbs provide secure, reliable, high-performance wireless networks in which everything can move. Now, each one of these descriptions, secure, reliable, high performance, 100% mobile, is individually difficult to achieve, and if you've ever tried to build such a network, then you've seen that for yourself. Achieving all of them at the same time is an extremely hard problem, and that's what makes it interesting and fun for Rajant. We call this type of network a kinetic mesh network. Rajant's kinetic mesh networks use a proprietary peer-to-peer networking protocol we call InstaMesh, and this provides extremely fast responses to network topology changes. We've been using InstaMesh for almost 10 years now. It works very well, and we're still improving it. Even though InstaMesh is proprietary, it's standards compatible. We use 802.11 standards for our physical layer, and our protocol routes packets at layer 2. Basically, if your data can be sent over Ethernet, it can be sent over mesh. InstaMesh is a completely distributed protocol. It has no central controller, no central decision maker, no one node to make a big picture of the network. And that's good for two reasons. One, it takes time to build a big picture of the network. And two, if the network's always changing, that's a lot of information that's constantly in motion to keep that up to date. InstaMesh always prefers the fastest path to any destination. That's how we make all of our routing decisions, and it's based on the RF environment at the time at which the packet needs to be transmitted. In other words, we're making routing decisions on a packet-by-packet basis. And we do this by allowing each breadcrumb in the mesh to track its own RF environment and its own traffic statistics and share just a small amount of information with its neighbors. This approach allows us to make extremely fast local decisions and react immediately to changing RF and network conditions, and eliminates the idea of any single point of failure. Breadcrumbs are ruggedly built. They're protected from vibration, from shock, water, dust, and heat. Rajant has over a decade of experience with military and mining customers that are very tough on breadcrumbs, and our breadcrumbs hold up in the field. We've seen temperatures in the field ranging from -40 up to 115 degrees. Breadcrumbs kept going. Our breadcrumbs are rated to IP67, and we've had breadcrumbs encased in ice and continuing to operate and provide applications to the customer. What it boils down to is, if you want to keep your applications available, you need to have a reliable network. And if you want to have a reliable network, you have to start with reliable hardware. Rajant breadcrumbs use multiple radios and multiple frequencies. Our current models support up to 4 802.11 A, B, G, or N radios in a wide variety of combinations, and some of our available frequencies include 900 megahertz, 2.4 gigahertz, 5.8 gigahertz. Rajant has a soft license for 3.65 gigahertz in the US, and we've also sold radios in the license bands of 1.4, 4.8, and 4.9 gigahertz. Custom frequencies are also available. We have a military customer in a large evaluation who changed their requirement from 4.2 to 4.8 gigahertz at the last minute. We were able to turn around new radios, including new hardware, new software, new drivers, in about 90 days. This multi-radio approach is tolerant of interference and congestion. If you take a look at these two network diagrams here, let me just explain for a moment how to read them. Each circle in the diagram represents a node or a breadcrumb, and each line between nodes represents a radio connection. You can see here we only show two colors of lines, and in our examples this represents two different frequencies. As I mentioned before, we support up to 4 radios in each breadcrumb, but it's just easier to show with 2 lines. So as you're reading this, remember that you can have up to 4 or potentially more connections between nodes. The network on the left represents a well-connected Rajant mesh with lots of redundancy. But imagine a local interference source in one part of the network, represented by the star on the right-hand side. If there's interference on the red channel in this example, then locally around that interference source, that channel may become unusable. But as you can see, there still is a usable frequency, and away from the interference source, both channels are still available. So in the case of some local interference, the network may lose some capacity, but still work. Having multiple radios also increases the usable spectrum and just gives us more bandwidth we can use to deliver applications. Again, the two network diagrams show the same network. The one on the left is a 2 radio network. The one on the right is a 1 radio network. The one on the left obviously has about twice the available bandwidth. Breadcrumbs use all of their radios for all purposes, and they use all of their peer links to route packets. If you take a look at this network diagram, this represents a traditional wireless network. This is not a Rajant kinetic mesh network. In a traditional wireless network, you have two kinds of nodes. There's infrastructure nodes, represented by the orange circles in the corners of this diagram, and you have mobile nodes, represented by the blue circles. And these two different types of nodes have different functionality. The mobile nodes don't route, they only roam between infrastructure nodes. And even if the network uses multiple frequencies, like this one does, they're not efficiently used. The mobile nodes use one frequency to talk to the infrastructure nodes, and the infrastructure nodes use a different frequency to talk to each other. So by not using these multiple frequencies as efficiently as possible, this network is really missing an opportunity for more bandwidth. Basically, dedicating frequencies to a single purpose reduces performance dramatically, not just throughput, but also reliability. An infrastructure node, for example, can't receive from one peer, one other infrastructure node, and transmit to another one at the same time, because a radio can only receive or transmit. In a Rajant kinetic mesh, all nodes are equal and all nodes route. And not only do all nodes route, but all nodes route via multiple peer connections on each radio. So there's no centrally managed tree overlaid on top of potentially usable connections. This is all local decisions made based on local information available to each breadcrumb. And these local decisions are immediate. A node can receive a stream from one peer and forward to another one on a different frequency at the same time. This gives us very low latency, on the order of half a millisecond per hop. And again, every node is just a peer. They're all equal. So going back to the traditional wireless network architecture, consider the mobile node in the upper right corner. How many potential routes does that node have to the application server on the left side of the screen? By the way, below that application server is just an Ethernet switch represented by that SW box. As you can see, that mobile node only has two paths back to the application server. First, the data has to travel to its local infrastructure node. Then it has to travel either clockwise or counterclockwise to get to the exit node, pass through the switch, and reach the application server. So there are two separate paths. On the kinetic mesh, however, the same node has any number of paths back to the application server. In fact, too many to count. Now consider, on a traditional wireless network, two mobile nodes who need to communicate directly with one another. In this architecture, they each have to communicate via an infrastructure node. That's two hops on the same frequency. This increases both administrative traffic and client traffic and is very susceptible to interference on, in this case, the green frequency. Consider the same situation on a Rajant kinetic mesh where two mobile nodes need to communicate with each other. In this example, they have direct connections to each other on two different frequencies. That's two paths to communicate directly with one another. And if neither of those is the best path, they have other options as well, communicating through other nodes. So there are many multi-hop alternatives as well. And as I mentioned, in a Rajant kinetic wireless mesh, all radios are available for all functionality. That doesn't include just mesh functionality, that also includes wireless access point functionality for clients. So laptops, tablets, phones, whatever, may associate with any node on the network if they're configured properly. So using all available frequencies and paths for all functionality gives us very high performance and very high reliability and allows us to adapt to changes immediately. And all of this happens automatically, requiring absolutely no administrative intervention. Rajant breadcrumbs move data fast. If you take a look at this traditional wireless network again, what do you suppose happens to throughput as the number of application server clients in the upper right region of the screen increases? Well, first of all, throughput to the access point provided by the infrastructure node is shared between all the associated clients. So those four clients are all sharing RF space on one frequency. Secondly, the backhaul traffic is bridged on one frequency all the way back to the application server, so you have potential bottlenecks on both frequencies. On a Rajant kinetic mesh, with the same scenario, you have no specific bottlenecks. There's more available routes, more available frequencies, and each stream is using the best or fastest route available for each packet. A Rajant kinetic mesh provides a high bandwidth network with low latency, which results in an extensible network capable of supporting multiple applications simultaneously. This is a departure from a traditional application-specific network approach, which results in redundant and underutilized infrastructure. And with full support for VLANs and prioritization, it's very easy to support multiple applications simultaneously. And as an example of our speed, one of our customers has a mine with over 230 nodes. Throughput measurements taken at all points throughout the mine never went below 10 megabits and were generally over 20. Now this brings us to one of Rajant's big differentiators, which is our focus on mobility. Now, what does Rajant mean by mobility? Well, to Rajant, mobility is just about any physical change to the network. It might be motion, it might be introduction of new breadcrumbs, it might be removal of breadcrumbs, it might be a changing RF environment, and all of this adds up to what we call a kinetic mesh network, which we handle very well. In a traditional wireless network, what happens when this infrastructure node fails? Well, as you can see, communication is lost to every node in that region of the network. This is a single point of failure, and it's a big deal. In a Rajant kinetic mesh, what happens when the same node fails? In this case, the only node that's become unavailable to the network is the node that has failed itself. This is no single point of failure, and usually no perceivable impact on the network if this happens. One of our customers has a mine that lost several infrastructure nodes at the same time due to a power issue, and there was no operational impact at all. In fact, it took them some time to realize that a good portion of their network was turned off. Now, on a traditional wireless network, what happens to local application server clients when this node experiences congestion or interference on either frequency? Well, application performance becomes poor or even fails completely. But on a Rajant kinetic mesh, when the same node experiences congestion or interference, there's really no perceivable impact because alternate routes are utilized immediately. Now, in a traditional wireless network, what happens when this node moves out of range of its current access point? Well, first, it's going to lose connectivity. Then it has to try to connect with another access point, and if successful, then the network has to reconfigure a little bit, and so you end up with a temporary loss of communication. With a Rajant kinetic mesh, however, what happens if the same node moves? Well, first, there's no loss in connectivity because a breadcrumb maintains all possible connections dynamically. This is a make then break approach, so it maintains a full set of options at all times, and it selects the fastest connection possible. As it moves, new connections become available, and only when they're better than the alternatives are they used. So application performance is constantly optimized on a Rajant kinetic mesh. Now, how well does a traditional wireless network adapt to changing coverage requirements? Well, if you need coverage in a different area, then generally you have to reposition your infrastructure nodes or add new infrastructure nodes. On a Rajant kinetic mesh, how does the same network adapt to changing coverage requirements? Well, if anything needs to move, it's trivial to do so, but generally you can use your mobile nodes as infrastructure without having to worry about anything. Consider this diagram, which is an analysis conducted at one of our commercial mining customers using a site survey tool. And what we did is we drove around the mine, and you can see the trail of the vehicle on the map here, and we measured the signal-to-noise ratio to the nearest infrastructure node. Now, on a Rajant mesh, an infrastructure node is just a label you can apply to a node. It doesn't behave any differently from others, but sometimes it's useful to label them. You can label them infrastructure, or truck, or shovel, or convoy, or whatever you want. In this diagram, we're measuring the link quality to the infrastructure nodes. So this is really how would the network look if it were a traditional wireless mesh network, where you needed to worry about mobile to infrastructure connectivity. Now, the same diagram and the same data set measuring the link quality to mobile or infrastructure nodes, really to any other breadcrumb in the mesh, shows much better coverage. This demonstrates the improvement in coverage characteristics when mobile nodes are able to route. Embracing mobility is the key to a successful mesh network. Rajant's mesh networks automatically adapt to network changes, and this provides a reliable network with no administrative intervention. Breadcrumbs can form mesh connections over Ethernet links. Here we have a modified diagram of a Rajant kinetic mesh with 3 Ethernet switches marked by dark boxes. And in this diagram, consider them all to be on the same network segment. The best thing you can do for a wireless network is to get packets out of the air and onto a wire, freeing the spectrum for other traffic. And by making mesh connections over Ethernet, we enable that. This allows for multiple ingress points, in fact, unlimited ingress points, and automatic failover if there are any issues with the Ethernet network itself. Now, this gives vastly improved performance because it treats wired connections as alternate wireless links, and because we route based upon how fast we can send data, we preferentially route through the Ethernet links in general. Now, because Ethernet links can be so fast, this effectively turns Ethernet meshed breadcrumbs into magnets that pull traffic out of the air and put it on the wire. This is useful not just for reaching wired devices like an application server, but can also be used to get traffic from one side of the mesh to the other, bypassing many wireless hops. Basically, meshing over Ethernet improves performance, eliminates bottlenecks, adds redundancy and reliability to a network, and makes it easy to extend. Breadcrumbs operate at layer 2 of the network model. And what this means is that you can consider the entire set of breadcrumbs in a mesh as one big virtual Ethernet switch. You can use breadcrumbs to bridge into vehicle or equipment networks. You can use them to bridge into other networks. You can use them to connect to other breadcrumbs. And because we operate at layer 2, it makes integrating with other equipment trivially easy. Any protocol you want, IPv4, IPv6, if you have encrypted Ethernet frames, whatever you have, if it'll run over Ethernet, it'll run over a mesh. You can even use this to extend your network using other technologies like microwave or satellite. Operating at layer 2 makes extending a mesh and integrating applications simple no matter what networking protocols they require. Breadcrumbs are shockingly compatible. Rajant breadcrumbs are secure. We have military-grade security options, in fact. We can encrypt packets to ensure privacy using AES with a variety of key sizes and AES modes. We have per-hop authentication for protection from packet injection or replay attacks. And we can even encrypt the MAC addresses of your traffic for protection from traffic analysis. We also support what you might expect for wireless client authentication and encryption, everything from WEP up to WPA2 Enterprise or Radius. And for the enterprise options, we support a long list of EAP methods. Rajant security options protect your data and your network. Rajant breadcrumbs can form very large and very dense networks. Bingham Canyon's Kennecott, Utah Copper Corporation has been in production since 1906. It's 0.6 of a mile deep, 2.5 miles wide, it's 1,900 acres in size, and they've been a Rajant customer since 2006. Their network consists of over 250 nodes. They're running 15 applications simultaneously, including fleet management, machine health, seismic monitoring, and dewatering. They have a very rough environment ranging from -40 degrees to 115 degrees Fahrenheit, and they have a 24/7/365 operation. Even with all of that, their network performs with less than 10 milliseconds of latency, 5 nines of uptime, and they've even upgraded their network firmware with 0 downtime. Rajant scalability helps you to extend your network, allowing you to adapt to growing needs with minimal administrative intervention. Rajant provides all the software tools needed to sustain your network. BC Commander is a desktop application that runs on Windows or Linux and is used to manage, monitor, troubleshoot, and design Rajant kinetic mesh networks. It's capable of taking a diagnostic snapshot of the network, which can be processed by another tool we provide called NAC. NAC can be used to look at the big picture of your network, compare configurations, look for noise issues, things like that. NetCrumbler is a network latency mapping tool that correlates ping results to GPS coordinates. Cacti is an open source tool that we've customized to provide network statistics gathering and historical trend analysis of network statistics. Rajant provides an appliance called an RADS that includes all the software I'm describing right now, and if you allow it, allows Rajant to remotely connect to monitor and manage your network for you. We have a language-neutral API called BC API used to access all of the breadcrumb functionality. Anything that you can do with BC Commander, you can do with BC API. And we have a number of smartphone apps in development for managing and monitoring different aspects of the network as well. This screenshot of BC Commander shows one of several available views, which we call the Bullseye View. In this view, you can drag one or more breadcrumbs to the center circle, and all breadcrumbs that are one hop away are in the next concentric circle outward from there. All breadcrumbs one hop away from those are in the next concentric circle outward, and so on. And this gives you a view of the best case hop count from any node to any other node in the network. This is some of our NAC output, which is used for analyzing the mesh network snapshots I mentioned. Here you can see a noise analysis of infrastructure nodes on 900 megahertz, 2.4 gigahertz, and 5.8 gigahertz. NetCrumbler, which correlates ping results to GPS coordinates, provides a Google Earth export for visualizing your ping latency throughout your network. And Cacti provides historical graphs of many different aspects of your network. Rajant's management and monitoring tools are there to ensure the most reliable, sustainable, adaptable, and high-performance network possible.
For more information, visit www.rajant.com.